Morning, everyone. Today's lecture will be on projective geometry, and we shall discuss some of the topics which are like vanishing points and lines. We'll learn about these points and lines, and the aim of today's lecture is to give you an idea of how to extract some useful information from a single image, or a geometry information, or recover geometry from a single image, right? And in future, what will happen? We will bring another camera. We'll introduce another camera, right? And we will study about the stereo vision system. But that's the topic of our next week's lecture. Okay, so the other topic that we will discuss is the projective invariants. So if you are trying to recover something from a single image, you need some measurements which are invariant. And invariant means that don't change, right? So we are interested in those measurements which stay the same, right? And then we will discuss cross ratio, which is one of the very important property, and measuring the height of objects from a single image. We'll see how to use vanishing points, vanishing lines, and all these concepts of projective geometry to measure the height of object. Then we'll look into homography, and finally image rectification. Now if you look at this image, can you work out the geometry of this image? What do you see here? Lines, that's correct. So we have two parallel lines, right? That represent sides of the jetty, right? But if you look at the planks, yes, there could be multiple lines. But if you just look at the edges, then you have two parallel lines here, right? And what do you understand from these lines? If you look at the image and if you draw some lines along the edges of the jetty, these two lines actually meet at one point. So they are converging at one particular point, right? Now, if you look at this ancient painting, it's from 1460 AD. This also gives you an idea that people of that age were well aware of these sort of concepts. Okay, so if an object is closer to you, it is bigger in size, and as it moves away from you, it slightly gets smaller. So if you look at the trees, they are parallel, right? But if you look at, let's say, infinite ground plane, these trees are shrinking, right? So in fact, the painters of that time, they also had this information in their mind, right? Because cameras were not there, and only painters were there to produce your real world images, right? And those people were also aware of these concepts, actually. That parallelism, shrinkage of images as it moves away from you, the object that as it moves away from you, if it's at a longer distance from you. Now, if you look at this particular image, can you work out the geometry of this image? So look at the floor or the ground. You have multiple parallel lines here with the squares, right? You have multiple parallel lines, and some of the lines are orthogonal to each other. Then the horizontal vertical lines, I must say. There are so many horizontal vertical lines here in this image. And are there any parallel vertical lines? Yes, exactly. We have multiple parallel lines here. It's exactly in this area of the. So we have these multiple parallel lines here. And then we also, you can think of parallel lines here in this area as well. The two parallel lines there as well, right? So why these parallel lines are significant? Okay, so why these parallel lines are significant? That takes us to an important topic like vanishing points and vanishing lines, right? So in perspective image, all parallel lines meet at a single point, and that single point is called your vanishing point, right? And multiple sets of parallel lines will give you multiple vanishing points. I have few slides to share that will actually help you to understand. We'll have multiple vanishing points. So if you let's going back to the first image, and if you're drawing, if you let's say find the edge of this image and draw parallel lines, these two lines will meet at one single point, and that single point is called vanishing point, right? And in the real world, like jetty is always, it's a sort of flat surface, right? Although it appears that this jetty is like, the lines are not parallel, apparently, in the image, right? There's a possibility someone has designed this sort of jetty, but mostly, you're well aware of the jetties. They don't converge in the end. Their size remains the same, right? The width remains the same. So assuming that we have those two parallel lines, they converge at one single point, and that single point is called vanishing point. Okay. Now, if you look at this old painting, it's from 1514. So the painter was also well aware of this parallelism of, right? He knew that, okay, parallel lines could be there and they carry some meaning. For example, let's say if you look at the height of the pillars in our daily life, yes, these pillars are almost the same, right? And then if you look at the parallel lines, let's say look at these platforms or footpaths, whatever you call it, you have some parallel lines from here that meet at some single point. Then if you look at the buildings at the back, there are a few parallel lines there as well. And all these points meet at single point, that's called your vanishing point, right? So even before the invention of the camera, people were well aware of these concepts, right? And at the moment, these vanishing points, vanishing line, these topics have been well researched and well established topics in computer vision, right? Okay, now talking about this particular image. So when you extend your parallel lines, they converge at one particular point. That point is called vanishing point, and that vanishing point can be outside the image. Okay, it's not necessary that the point should be inside the image, could be outside the image as well. And we'll see that in the next few slides when we'll convert some of the parallel lines. Okay, so coming to vanishing line, joining two vanishing points give you a vanishing line. Now if you look at this image, you have different parallel lines here. And if you extend those parallel lines, those lines will converge at one point. And if you look at the image, you have one vanishing point on the left and another vanishing point, which of course is not visible here on the right side of the image. And if you join these two vanishing points, you get a vanishing line, and that vanishing line has been represented by a blue color, right? By here, blue color. So vertical parallel lines give a vertical vanishing point, and vertical vanishing point in this particular case is at infinity. If you can see, again, they meet at some far off point. All these parallel lines converge at some far off point, and we say that, okay, that point is at infinity. So any questions so far on vanishing point and vanishing lines? I think they're pretty straightforward concepts. Now, what do you think, why these two things are very important in computer vision? What is the significance? They help you to determine perspective. Yeah, that's correct. What else? Any application?
Measure parts.
Yeah, that's absolutely right. Here you can measure height of the object, and yes, we'll discuss that example in today's lecture as well. So before moving forward, I'll just share, I just found this video of, it's about vanishing points, and they have implemented their technique in MATLAB, and they determine there are some parallel lines here, some horizontal parallel lines, some vertical parallel lines, and then they project these lines on a sphere, right? And then they extend these lines to find some vanishing point. I think this is a very good way of visualizing your vanishing points. So we have a vanishing point here. We have another vanishing point here. Then again we have some vanishing points here. And what will happen if you join these two vanishing points? What will you get? A vanishing line, right? And as we have multiple vanishing points, we'll get multiple vanishing lines here, right? Okay, now coming to the image plane. You have three horizontal lines in your real world, right? In the real world, we have three parallel lines, A, B, C, D, and E, F. If you project these lines on the image plane, they will no more appear as parallel lines. And the same is true if you just remember that Jetty's image. In your real life, the edges of the jetty are parallel, but when you take an image, they appear to converge at one particular point, right? So if you project your parallel lines on the image plane, they will no longer appear as parallel lines. So the projection is shown by lowercase a, b, c, d, e, and f, right? And of course, you have your optical center there. And when you extend these lines that are on your image plane, you extend them and they all converge at a vanishing point, right? And as I've told, this vanishing point can be outside the image. So A, B, C, D, E, F are actually the lines on your image, right? And yeah, and vanishing points are often outside the image boundary. Now this one is a more obvious example. So you have, just think about a jetty, you have a jetty there and you're taking an image of the jetty, and the projection of those lines will appear on the image plane the way they have been shown here, right? So the two parallel lines will appear to converge at one particular point in your image plane, right? Any question on that? So of course there are some obvious things. Okay, now there is one special type of vanishing line, and that line is called the horizon, right? So parallel lines that are not orthogonal to the optical axis meet at a vanishing point, right? Of course all the parallel lines converge at a vanishing point. And then two sets of parallel lines on the ground plane will give two vanishing points. So you have a set of parallel lines here in this direction. They converge at this particular point, right? Then you have a set of parallel lines here. They converge at that particular point. And these lines are not orthogonal to the image plane, right? And these two lines give you, these parallel lines give you two vanishing points. And if you join these two vanishing points, what do you get? A vanishing line, and that vanishing line is called the horizon, right? These lines are called the horizon. And just look at the first statement. That is very important to define a horizon. So parallel lines that are not orthogonal to the optical axis meet at a vanishing point, right? So if you have these sort of lines, you find your vanishing points, you join those vanishing points to get a vanishing line, and that vanishing line is called the horizon. Okay? Okay, now coming to the planes, a set of parallel planes that are not parallel to the image plane intersect the image plane at a vanishing line. So the two lines converge at a single point. Parallel planes converge to give you a line. So reduction in dimensionality, right? That's a reduction in dimensionality. So the horizon is a spatial vanishing line when the set of parallel planes are parallel to the ground reference, right? So given multiple planes, if you extend those planes towards your image plane, they all will appear to meet at one single line, right? So just keep that in mind. Lines converge to a point, planes converge to a line. So it's all about the reduction in dimensionality, right? Any questions so far on that one? I think these are pretty easy to understand things, right? Okay. Now the next question is how to calculate vanishing points and vanishing lines. So let's say a point in image is defined by its UV coordinates. So we sometimes replace this UV by X and Y, and I believe you all know how to get that X and Y information, right? So row and the column information in your image matrix. It's pretty easy to extract that information using MATLAB or any other language that you're using. So 2 points determine a line. We already know that, right? And then intersection of 2 parallel lines will give us a vanishing point. And 2 vanishing points will give us the corresponding vanishing line. So let's say you click on 2 different points on an image, right? And once you have those 2 points, you can always determine a line, because what do you need? You just need 2 points to get a line. You click on image at 2 different points, you get a line, right? You get 2 different points from image, join those 2 points, you get a line. You do the same for another set of points, you get another line, right? And then 2 vanishing points will give us the corresponding vanishing line. So you, let's say, first of all, you get 4 points on 2 parallel lines. You extend those lines, they will meet at some vanishing points. You do the same process for another set of points to get another vanishing points. And once you have information about those vanishing points, you can easily define a line. Because to get a line, what you need? Just 2 points, right? Just click on the image, right? So what does it involve? 2 clicks on each parallel line will solve the problem, right? 2 clicks, because each click will give you 1 point, right? And 2 points define your line, actually, right? And now, this is a manual process. So if you want to do it automatically, how would you do that? Using edge detection. You guys have already studied that in your second lecture, I believe, right? And then Huff lines will solve the problem. You can do it automatically in MATLAB, and some built-in functions are already there to help you guys solve these problems, right? Okay, now when it comes to the calculation of these things, we normally look into homogeneous coordinates. So what happens in the homogeneous coordinates? You have X and Y values, X and Y coordinates, and you have 1/3 value which represents the scale, and normally it's set to 1. And points in 2D are represented in homogeneous coordinates as a 3D vector, X, Y, and 1, the way it has been displayed here, right? And points and lines are dual in 2D. What does it mean, dual? Any idea? Okay, the next slide will help you to understand that. What does it mean? Lines and points are dual in 2D, right? So next slide will help you guys. So lines are represented in homogeneous coordinate as 3 vector also. So it's represented by A, B, and C. And homogeneous coordinates contain redundant information. The representation includes an arbitrary scale. So a point 231 and 462 represent the same point 23 in homogeneous coordinates. Why is that? So you divide your second point here by 2, right? So divided by 2, you get 1 there. So you're left with 2 and 3 as your actual point in the image, right? This is the same, it's 2 different representation of the same point. But just make sure your last scale value takes care of that, right? So if let's say you're representing it by 6, 9, then your last scale value should be 3. Yes. Yeah, that's true, that's true, that's true. Right? So just the representation in your homogeneous coordinates. Just make sure that scaling in the end is very important. And you just divide that by by the last number to get your actual image coordinates in the inhomogeneous coordinates, right? Now similarly, the line like 4, 7, minus 3, 2, 3.5 and minus 1.5 represent the same lines. 4x plus 7y minus 3 is equal to 0. Or the same, the other one gives you another equation of line which is 2x 3.5y minus 1.5. These two are the same lines. So how do you know that these two are the same lines? Any idea from your high school mathematics, algebra and all that? It is, but how do you know that these two lines are the same? How will you prove that? Yeah, that's one of the ways. And talking specifically about the lines, you can calculate the slope, and you'll find that the slope is fine, and will be the same. And then you can always find the x and y intercepts, right? From these equations, they will give you the same values, right? So in homogeneous coordinates, these two are just 2 different representations of the same line. Now, how will you determine that a point lies on a given line? Given a point and a line, how will you determine that a point actually lies on that particular line? Mathematically, or you can, let's say, if you're implementing it in MATLAB or some other, in C or whatever I am. Okay, to determine if a line L passes through a point P, x, y, and 1, check if their dot product is 0, right? So if their dot product is 0, the line passes through a point P. And let's say if you take this product and it's equal to 0, it indicates that L passes through P. So let's say there's an example as well. So given a line 2, 4, 5, so 2x plus 4y minus 5, right? And it contains the point 1.5 minus 2 and 1. And since this line passes through the point, you just take the dot product and you get 0. And let's say if you're clicking on the image to find whether the line passes through the point, will you get 0? If you don't have exact value of the coordinate, you're just clicking, it's an approximation. So will you get 0 as a dot product? No, right? This value won't be 0. So you'll have to leave some space for error. So some sort of tolerance should be there. If you have the exact value, yes, of course, this dot product will be 0. But if you're just clicking on the image, these are just random clicks, or let's say, because you don't have the exact value, you just have approximate values of the coordinates. So this dot product in real life won't be 0, it will be somewhere close to 0. So you'll have to keep some tolerance there, some space for error there, okay? Now, the line L that passes through 2 points P1 and P2 is obtained via the cross product. So you take cross product of 2 points to get a line, right? You can, yes, of course, you can do it on a piece of paper, and in MATLAB you can do it in one-line statement. Which function will you use to find a cross product of 2 points? Yeah, that's matrix multiplication can give you that, but what specific function in MATLAB will give you a cross product? That's cross. Cross is the name of the function, right? Just give two different points to that function, and it will give you equation of the line, right? And in normal mathematics, you take cross product of 2 points, that gives you a line, right? Now the line L passing through the point 0, 2, 1 and 3, 0, 1 is given by this particular equation. You just take the cross product of these two vectors, and each vector has the coordinates of the points, and of course the last value, these are inhomogeneous coordinates. The last value is the scale, and when you take their cross product, you get the equation of the line. Just try these values in MATLAB and you will get 2, 3 and minus 6 in your output, right? Or do it yourself using the cross product rules and you'll exactly get these values. Okay, now finding the intersection of two lines. Since lines and points are dual in 2D, we obtain the line coordinates the same way as before. The point of intersection of two given lines is obtained by the cross product. So now here comes the explanation of that terminology dual. So you take cross product of 2 points, you get a line. You take cross product of 2 lines, you get a point, right? So cross product is giving you a point, and the cross product of 2 lines is giving you cross product of 2 points is giving you a line, and the cross product of 2 lines is giving you a point, right? That's why we say they are dual in nature. So we have an example and one exercise question here. So if you're given 2 lines, 462 and 201, and let's say they intersect as 60 minus 12, and which corresponds to the point minus 1/2 in the homogeneous space. Why 60 minus 12 has been represented by minus 1/2 and 0 in inhomogeneous coordinate? So the 2 lines 462 and 201 intersect at a point. When you take their cross product, they intersect at a point 60 minus 12. But in the inhomogeneous coordinate, this point is actually minus 1/2 0. Why it's minus 1/2 0?
Sorry, 6 is divided by -12.
Yeah, that scaling factor is minus 12. So you are dividing it by the last value, because that value should be 1, right? So you divide it by minus 12, you get minus 1/2 and 0. 0 divided by minus 12 will give you 0. Yeah, that's correct. So you guys have one exercise question as well. You can try it later maybe. Okay, so any questions so far? All good? Okay. Now, can you find the equation of the vanishing line in this image? So it's a pretty simple operation that you need to do. So you click on the red dots, right? Which one? Let's say on your line number 1, you click on 2 red dots to get 2 different points. 2 different points, you click on 2 red points to get the first line. Then you click on the green points to get the second line, and you find their intersection. How do you find the intersection? Cross product of these 2 lines. That's absolutely right. Then you do the same for the other set of lines, which are actually perpendicular to your first set of parallel lines. Right? You find 2 points on the first line, you click on 2 other points on the other parallel lines, you take their cross product, you get another vanishing point. And the cross product of 2 vanishing points will give you a vanishing line. That's absolutely right. So pretty simple operation there, right? Just few clicks, and that gives you your vanishing points and vanishing line in an image, right? Now, what can we find from the vanishing points and lines? We have been discussing vanishing points, vanishing lines, how to calculate vanishing points, how to calculate vanishing lines. So let's say we have all that information. We now know how to calculate vanishing lines, vanishing points. Now, what next? What can we find from all this information? Okay, so this displayed slide is actually showing you an abstract from Crimsey's PhD research thesis, right? His PhD thesis. His thesis was actually on this particular topic. And what he says, given the horizon, you guys already know horizon, it's a special type of vanishing line, right? Given the horizon, the vertical vanishing point, and one reference height. The height of any point from the ground plane can be computed by specifying the point and its projection on the ground plane on the image. As the gentleman was saying, you can calculate the height of any object if you already know the reference heights, right? So this topic was well studied in 1998 by Crimsey, right? So given the horizon, the vertical vanishing point, and one reference height, you can calculate the height of any other object in the image. And we have one demo on this one, and we'll discuss how to calculate this height in the next few slides, right? But just keep this definition in the mind. Given all this information, we can calculate the height from the ground plane. Now, let's take an example of human height measurement. So if we know the height of one object in the scene, we can find the height of a person using vanishing points. Right, so we have been discussing vanishing points and vanishing lines. Here comes their application. So let's say we already know the height of the telephone booth, right? You can Google it, and it will give you all the dimensions, size, and of each dimension of this telephone booth. I know it's a very famous landmark of UK or London, right? So you can get the height by just Googling it, right? And keeping that height as your reference height, you can find the height of the person in that particular image. How to do that, we'll discuss in the next few slides. That reminds me, actually, one of the professors in ANU actually worked on this particular topic on height calculation and all that. And someone in the US was on the death row, and the professor went to the court, and by measuring the height of the individual, he actually argued that, okay, this person was not there at the crime scene because his height is this much while the height of the person in the image is this much. So what he did, he actually used some reference heights from the image, and then he tried to measure the height of that particular person, right? So heights are normally in centimeters, and let's say if you're calculating some height from an image, and if you go and find the height of the actual person, that you will find that it's actually exactly the same, right? Now, before measuring the height, we need to take care of some properties that actually don't change an image. We are trying to recover geometry from a single image. That's what we said at the beginning of the lecture, right? We are trying to extract some useful information from a single image. So we have to be very careful. We have to look into all those parameters that don't change. We have to look at all those measurements that don't change. So Euclidean transformation is one such thing, one such transformation, which is represented by a rotation matrix and a translation matrix, right? And collectively, as shown here for 2D and 3D case. So it just takes care of rotation and translation. If you know that how much the object has been rotated by how much angle, you know how much it has been translated, then you can easily use this transformation to recover the actual shape of the object. Similarly, you have a similarity transformation. The only difference is that now you have a scale there, right? So the last value is S, which is scale, which could be any value starting from 1 to 10 or any other value, right? Two other sort of transformations are affine transformation and projective transformation. But instead of using R and T and using X here, because in these particular transformation, they are not just the rotations and translations, there are some other properties or some parameters or values as well there. What are all those things? They are covered in the next slide, right? So these are a few important transformations that you have to keep in mind. Now, what changes and what doesn't change with these transformations? So if you talk about you have been given an original scene or original image, right? So your similarity transformation preserves all the angles, right? Even if you rotate the object, the angles will still stay the same in the similarity transformation. Then ratios of lengths remain the same. Your ratios of area, parallelism, all that stuff remains the same, right? Similarly, so your similarity transformation takes care of rotation, translation, and the scale, right? Now coming to the affine transformation, it deals with the shear and distort aspect ratio, right? And what does it preserve? Ratios of lengths, ratios of areas, parallelism, and 3 other properties, and that we will discuss them in detail. And finally, coming to the perspective transformation, it handles projection with a finite focal length. And what does it preserve? Concurrency, collinearity, and cross ratio. If you look at these 3 properties, they are common in all the 3 transformations, right? And that's why they're very, very important now. So what is concurrency? In terms of lines and points, what is concurrency? So if 2 lines converge at a point in your real world, these 2 lines will also converge at the same point in your image plane, right? That's concurrency, right? So 2 lines in your real world converge at one point, those lines will converge at the same point in your image plane, right? What is collinearity? So multiple points that lie on the same line in your real world will lie on the same line in the image plane as well. That's your collinearity, right? And what is cross ratio? We'll discuss that in more detail in the next few slides, right? Because that's again a very important property for recovering information from the images and all that. Okay, now cross ratio is the most important geometric invariant for projective transformation, right? And what you need to do is, for calculating your cross ratio, all you need is 4 points on a line, right? So given 4 points on a line, say A, B, C, and D, you take, let's say, x1 as the first reference point, right? X1 could be your, let's say, point A in this particular case, and you measure a distance from, you take point A as your reference point, you measure a distance from point A to point C, and point A to point D, and you take the ratio. And then you take another point, let's say point B, and you measure the distance from point B to point C, and point B to point D, and you take the ratio of that distance, right? And then cross ratio is the ratio of the ratios, right? You can see it's the ratio of the ratios. So ratios can change in the image, but the ratios of ratios don't, right? That's why we say cross ratio is invariant property, right? Because ratios of the ratios doesn't change. Now the another important thing is the 2 reference points and the ratios can be arbitrarily chosen. So you can shuffle the points. So instead of B, C, B, D, you can use C, D, and C, B. And then you can also change the ratios. You can use instead of R1 by R2, you can take R2 by R1. So if R1 and R by R2 is preserved, of course R2 by R1 will also be preserved, right? It won't change. Now in the case of cross ratio, there are actually 24 permutations of possible cross ratio values. However, these values are repeated, leaving only 6 unique cross ratio possibilities, right? So there are only 6 unique cross ratio possibilities, which are discussed in the next few slides here. So now we have said that cross ratio is invariant, right? Here is a small proof that actually supports this argument. So let's say you have 4 points on a line A, B, C, D, and then you have an image plane and you project these points on the image plane and you get A dash, B dash, C dash, D dash. This image plane could be anywhere, right? At the moment it's just tilted there, but you can put it anywhere in front of these lines, right, and take the projection. Now, I believe you know that the area of a triangle, now here we have different triangles here, right? So talking about the triangle AO and C, the area of a triangle AOAC, which is given by half times the product of two sides here and the angle, sine angle, right? It's a simple mathematical equation. I believe you guys already remember that from your high schools, right? Okay, so using this particular equation, this particular formula, you can find the height of, you can find the area of triangle AO and C, area of AO and D, BO and C, BO and D, right? And if you substitute all these values there in the equation, and you will see that some of the terms will cancel out. Let's say the OA will cancel out there, and OC will cancel out with the next term. Similarly, your OB will cancel out with OB, OD will cancel out with OD, and you will just be left with sine of the angles. And as we have said that angles don't change. So if angles don't change, that means cross ratio is preserved, right? It's invariant property of the image, right? So cross ratio depends on the angle and is thus invariant under projections, right? So these are simple, pretty simple mathematical calculations, right? You just find the area, chuck in the value in the formula and solve that, and it gives you this sine expression. And if you're interested in looking into the detailed derivation and all that, I have provided the reference there as well. It's from What is Mathematics. It was published back in 1998. It's a pretty old concept, right? So you can look into details if you're interested. You can easily access all these articles from me if you log in here at UWA from your student account. Now, cross ratio of equidistance points, how will you calculate that? So you have 4 points A, B, C, and D at equal distance. You take point A as your reference point, right? And you measure the distance from A to C and A to D, and you take the ratio. And then you take point B as your reference point. You measure the distance from B to C and B to D, and you take the ratio. And you then next you take ratio of the ratios, which is cross ratio. That gives you some value. Now this is the way of calculating your cross ratio. This just example just explains you how to calculate the cross ratio. Yes, you can always change the points. As I've told you, you can always change the ratio. So instead of R1 by R2, you can make it R2 by R1, right? You can always swap. Now, I hope you guys are well aware of this image, this place. These are the, I think it's the front hall of UWA. It's in the Winthrop Hall. And so these points were calculated using the image information. So the cross ratio gave us 1.332. So what normally happens, the pillars are normally at equal distance, right? And they have the same height, so height is not important. We are just measuring the distance between the pillars. So they are normally constructed at equal heights. So these are equidistance sort of scenario. And these values were calculated using the image. But if you actually go to this particular location, and if you measure this distance and calculate the cross ratio, you will get exactly the same value. If not exactly the same value, somewhat close to this one. But all these calculations were done using the image, that single image actually, using all this concept of cross ratio. Okay. Now, coming back to the human height measurement problem. So if you know the height of one object in the scene, we can find the height of a person using vanishing points. Now, how to do that? So in this image, we have HR, TR, and BR. So HR represents the height of the reference object that we already know. The top point of the reference object. B is the base or the ground, or the point on the ground plane for the reference object. And then you have H, T, and B, the values that we want to calculate, the height of the person, or we sometimes represent by H of X or H of Y, something like that. But for simplicity, I'm just keeping like H, T, and B. So you project all these lines on your image planes. So two parallel lines in the image plane will appear something like this. They will appear to converge, right? If you remember that slide of 4 lines, A, B, C, D, D, E, and F, G, or A, B, C, D, and E, F, there were 3 parallel lines, and when you projected those lines on image plane, they didn't appear to be parallel in that image plane, right? So if you project these parallel lines, these H, R, H on the image plane, they will appear something like this. Now how to calculate the vanishing point? The first vanishing point P could be calculated by finding 2 points on your first parallel line and 2 points on the other line, right? And these 2 parallel lines, the cross product will give you a vanishing point. Now, as we are interested in calculating the height, another important thing is you find another set of parallel lines. So you join point B, R, and B. So in actual image, in your actual image, these points are at the same level on the ground plane, right? If you join these points and you extend them, then you project your top of the reference object on the other parallel line. So these TR and TR again, for a parallel line, if you're, let's say, projecting TR on the parallel line, it will appear something like point I, right? And then you join BR with B, TR with T, you get 2 parallel lines. And if you extend those, if you take cross product those 2 lines, what will you get? Point Q, right? So is this clear to everyone? Like you take projection of a point on the parallel line. It's clear? So these are 2 parallel lines, right? And let's say you extend this line a bit. You take projection of this point here, right? So you already know this TR. The distance of this TR from the ground plane, and if you extend it there, this one is giving you an idea about the point here. Point I is actually somewhere here, okay? The point I, this point I is somewhere here. This is the projection of this point here, okay? And then you take cross product of these points, you get a line, and by taking cross product of point B, R, and B, you get another parallel line. You get another line, and you take cross product of 2 parallel lines to get point Q. Now, next step is you take the cross ratio in the image plane, and which, yep.
Sorry, just so I can be sure. You work out that second vanishing point because you know both B values are on the same.
Exactly.
Then you can go and work out.
Yeah, exactly. See, these values are actually on the ground plane, right? And you already know this is reference. This is the starting point for your height. So yeah, that's absolutely right. Okay. Now taking the cross ratios, BI divided by BP. Again, you already know how to calculate the cross ratios, right? We take B as a reference point. We calculate the cross ratio from BI to BP. And then for the second point, we say we take a cross ratio. We take T as our reference point, and we take TI to TP as our distance. Now, if you translate these values in the real world, how will these distances be represented? The distance BI can be represented as I minus B, right? So I minus B will give you this distance, and this is basically BI, right? So I minus B basically gives you this height. And what is the value of B or BR here? 0, because the reference plane. Well, that's why in the real world scenario you represent it as I divided by P, because B is 0. It's on the reference plane. It's on the ground plane, right? Now, how about TI and TP? These values could be written as I minus T divided by P minus T. and you just in the next line is just another representation of the same expression, and then you split them into two different parts. Let's say p by I minus t by I minus t, another different mathematical representation of the same expression, and then you solve these equations, and in the end you get I divided by I minus t. And if you reshuffle these values for t, and that will give you I times Rw minus 1 divided by Rw. Now, what is t? The top point of the person, and you're trying to measure the height of that person. Now, if you represent these values in the real world scenario, what will happen? T is basically your h that you're trying to calculate. I is basically your hr. I is the projection of, I was the projection of this value, and this one whole represents your hr, right? So this, if you let's say 0, tr, what it gives you? 0 to tr gives you hr basically. So tr is just 1 point, br is 1 point. If you measure distance between those 2 points, that will give you your hr. Yeah, right? So hr your reference values, then you already know the ratios. So in the real world ratio, that will be represented by the cross ratio in the image domain. And using all this information, you will get the height of the object. So you need your reference object. All you need is information about the reference object, right? And then using this particular expression, you can easily get the height of the object of interest. Now, his algorithm, so as Cremonesi did all his PhD in this particular topic, and you can actually, if you're interested, you can read his paper. It's single view metrology, algorithms and applications. And I have provided the link, I believe, for this lecture in this week's What Do You Need to Know. If you just go to that particular material, you will find that link, okay? So if you're interested, he has explained all this height calculation stuff in his paper, right? And it's pretty easy to understand. Now, as he worked on this particular topic, he came up with a very stable algorithm. And I shall briefly discuss his algorithm here. He says that we calculate vertical vanishing point V, then calculate vanishing line of the reference plane. And the next step is you select the top reference point and the base reference point of the reference object, right? And compute a metric factor, alpha. You calculate this factor alpha using this particular expression. And you repeat this process for the other objects in the image to get the height of those objects, right? So that's a pretty stable algorithm that was proposed back in 1999. And using this algorithm, you can easily actually find the height of the objects in the image. We have one demo in the end of the lecture, okay? And that will give you actually idea of how to calculate all these information. And I believe if you search, you should be able to find a MATLAB code for this as well. Yeah. You should be able to find a MATLAB code for finding the height of these objects because it's all manual clicking. It's not automatic, so yeah, should be there. Now, coming to the measurement height. So the first step is radial distortion needs to be removed first. What does that mean? There should be lines and no curves actually, right? Because in measuring a height, you need a line, not a curve. There should be lines, no curves. Robust detection of parallel lines. How do you ensure robust detection of parallel lines? Or how could it be robust? If you're clicking on an image, probability of error is pretty high. So your clicks should be very, very accurate, right? Your clicks should be very, very accurate. Now, vanishing point detection based on multiple parallel lines. So you don't just use two parallel lines to find a vanishing point. You should find a set of parallel lines and then use those parallel lines to find a vanishing point. That will ensure that, okay, this point is more reliable in an image, right? And then heights are not always vertical. Ideally, the vertical line should meet at the vertical vanishing point. So you need to take care of this property as well. So height could be, let's say, if it's a tilted height, let's say, and the lines are parallel, then you need to take care of that particular feature as well, or the particular property as well. Okay, now as we discussed, there are 6 possible cross ratios which are represented by this particular expression. R, of course, is a cross ratio here. And then we have a special case. If let's say R is equal to half, then the 6 cross ratios are not unique anymore. Uniqueness means there is no repeatability, right? 6 unique values means they are different from each other. But when your ratio is equal to 1 by 2, these values are no more unique. And as you can see, there is a repeatability here, right? So, and this particular situation, this corresponds to the situation where one point is the midpoint of the other points, while the fourth point is the point at infinity, right? Just keep that in mind. When you get your cross ratio equal to half, it actually represents this particular situation where one point is the midpoint of the 2 points, and the fourth point is at the infinity. Image rectification. Can we just take 5 minutes break, guys? And we'll just continue from here. Okay, guys. So coming to the next important topic. Important topic is image rectification. So it is possible to remove perspective distortion of a plane in a scene if we can find the vanishing line of the plane. You guys already know that, how to find a vanishing line. And we have two reference measurement of known lengths and angles. We need to identify 4 points on the plane in this particular way. How to do this image rectification? I will discuss I'll explain them further in the next slides actually. Okay, so before going into the details of calculating the image rectification, I would like to discuss an example. I believe most of you are already aware of this area. You know this area, right? And what we are trying to do is we are trying to recover the shape here on the floor, which is a square, right? Where do we have squares here? This region, right? You can think of any practical application. For some practical application, yeah, this place was destroyed during World War II, and you guys are trying to reconstruct it as some ancient place, right? And you have some old images, and you're just trying to recover some information from geometry from that image. So just think about that. So you have some vanishing points, you have some vanishing lines, and then the points are used to provide constraints on the fine transformation. And when you perform your image rectification, you get this sort of view. Can you see the squares there? Right? So image rectification basically helps to recover that particular shape, that geometry from an image, right? And if you look at this image was taken from this particular point, right? And that's also evident in the rectified image as well, right? As you move away from the point where the image was captured, you see a blurry sort of stuff there, right? But actually you can see that in the rectified image you at least managed to get some information about the square shape of the tiles or the floor there, right? That's what image rectification is normally used for. Now, how to calculate this image rectification, how to perform all that? Now, in general, we need 4 points for rectifying a plane that has been distorted by a perspective projection. And now, if you remember from your camera calibration lecture, have you guys remember this matrix? Point M is a point in your 3D space, in your real world point, X, Y, and Z. SM is the projection of that point in the image plane. What was RNT matrix? Rotation and translation, exactly. And what is K? Intrinsic camera parameters, right? So now, if you represent this point M in homogeneous coordinates, you will add just 1 in the end, which represents the scale, right? So by 1 means these X, Y, and Z stay the same, right? In your homogeneous coordinates as well. Now we can expand the above equation using this particular in this particular way. Now you already know R and T is and it's a matrix. It has all the values of rotation matrix, all the values of your translation matrix. Now, for simplicity, we are considering a plane XY that's orthogonal to us. So we are setting Z equal to 0. And if you substitute Z equal to 0 in this particular matrix, you will be left with the simplified expression, which comprises of your R1 and R2 and just X and Y coordinates, right? And why we are substituting Z to 0? Because that also takes care of the distance of an object from your image or from the camera actually, right? So you're just handling the orthogonal thing. You're not taking care about the distance stuff, all that, right? Now this K matrix and your translation and rotation matrix collectively gives you a 3 by 3 matrix, which is called homography matrix, right? This matrix is called a homography matrix, and this matrix basically translates your real world information into image plane rectification, and this particular homography matrix helps you to rectify an image, right? So if you remember the concepts from your previous lecture about all these values, just keep in mind these two values together. This 3x3 matrix, homography matrix, actually helps you to perform image rectification, right? Now, calculating the homography matrix H. So the homography matrix has 9 unknowns and is defined up to an unknowns scale, right? So I hope you guys remember this expression as well. This one is also from your previous lecture, right? If you got a chance to look at the recording of your camera calibration lecture, this expression was given there. So again, the matrix on the left is the representation in the image domain. Then you have a matrix that maps your image, your real world information to a image plane information, and then x, y are again your real world coordinates, x and y coordinates. Now, with the simple calculation, you get the value of ui and vi. They have been explained in the previous lecture. But if you look at this matrix multiplication, what is S here? Just look at the calculation of S. How will you get S? You multiply third row of the first matrix with the second vector, right? Or the second matrix, you can say that, and you get H31 times xi plus H32 times yi plus H33, right? And if you look at SUI, now you already know your S, and SUI you can just multiply the first row of your first matrix with the xy matrix vector, right? And that will give you the value of ui and vi. So using these values of ui and vi, you can easily get this information. Now, writing it into a system of linear equations. Again, this thing was also discussed in the last lecture, in the camera calibration lecture. This one was probably on slide number 16 or 17. You can go back to that lecture, and these all things have been explained in detail there. So you get this sort of linear equations there, and now you have all your h values in one particular vector, and which makes your calculations pretty simple. If you have these sort of vectors, you can always check in these values into, you can give these values to MATLAB for calculation by using cross product and all that, right? Now, recall from the camera calibration lecture that a solution of this equation is the eigenvector corresponding to the smallest eigenvalue of the left matrix, right? So, brief concepts from the previous lecture. So, if you go through these particular slides of the previous lecture and try to understand this calculation, that will also help you to understand this one. Actually, this all is based on that previous calculation, right? Those previous calculations, and it's very easy to understand, very well explained there as well, right? Now, this is a special case which is called affine homography, and affine homography is a more appropriate model if the image region in which the homography is computed is small, or the image has been acquired with a large focal length. Now, affine homography is a special type of homography whose last row is fixed to H13 equal to H23 equal to 0 and H33 equal to 1. Now, if you talk about the practical implementation of this stuff, there are some built-in functions in MATLAB. You can use make T-form and imtransform that actually help you to calculate all these values in one step, right? So you can look at the help of this function. If you use these functions, they will help you to understand all these things, to give you all these values very easily, right? It's one-step process. Now, here's an example from the image rectification. Someone drew this square in the image, and they wanted to recover this square shape. So using the steps of image rectification, that homography matrix calculation and all that, they finally got this is square shape, this is rectified image, right? And it clearly gives you some information about the geometry, and we are interested in that square shape. So image rectification actually helps you to get this particular shape from an image. I have so this is, I think this video is from one of the application that actually performs image rectification. So what they do, they find parallel lines on the frame, and then they do some image rectification steps to get the shape of the frame. Like it's just few clicks gives you the shape of the frame. So they're just trying to recover the shape of this particular frame, right? Now similarly, using the same strategy, if you're interested in recovering some information about some shape or some pattern in a given image, you can always use image rectification to get that information, right? So that's just a brief video example of image rectification. So these are some of the, you can say it's a practical application you can use in archaeology or all that stuff, right? Now, so we have discussed that vanishing points, vanishing line, projective geometry, all that. Why is it significant? What can we do with all these concepts? So the first application, you can construct a 3D model from single views. So our discussion was just based on single image, right? We are trying to recover the geometry from single image. We are trying to extract some useful information from a single image. So using a single image, you can construct a 3D model. So what does it involve? You segment the scene. You remove unwanted objects from the scene. Let's say objects that are occluding, that are a bit complex. You remove those objects. And then you fill occluded area. So occluded area, let's say you have pillars there in that building, right? And if you capture an image, any part of the image that's behind that pillar will not be visible, then you can always fill that information, right? And then you can, of course, once we have a 3D scene, you can always rotate that. But the important thing here is you need planes, right? You need planes here for creating a 3D model. And planes you can get always, if you look at this image, you can get different planes from this image. And this actually strategy, this sort of procedure is used for, let's say, creating a 3D model of a city. You have one image of one particular location, and normally what happens, you have a flat road that gives you one plane. You can use it as a plane. Then you have different buildings in that image. You can use them as a plane to reproduce a 3D model for visualization purpose. So one image gives you all that information. Now, looking at this 3D reconstruction of historical paintings. So this, you have the painting on the left, using all these concepts of projective geometry, you reconstruct the painting. So if you look at the pattern, so number one, the complex objects were removed, right? If you look at the reconstructed image, all the these objects were removed. These have been removed here. Then you have a very nice pattern on the floor. And what does this pattern represent? Some parallel lines, right? These are some parallel lines here. And then you have some parallel lines here as well if you look at this window. So all this information was used for reconstructing this image. And then, of course, you can always fill in the required information for the reconstruction purposes. So if you look at here, so they just fill this information with the wall. No legs here, right? So they just filled it with the information of the wall, right? Of course, this part of the image is occluded here. And when you remove an object, you, of course, lose some information. Okay. Okay, so that brings us to the end of the lecture. We just discussed vanishing points and lines, projective invariance, cross ratio. We discussed how to use these vanishing points to calculate the height of an object in a single image. Then we discussed homography and image rectification. Image rectification can help you to recover some information about the geometry of an image. Before stopping here, I have one short video demo to discuss. Where did it go? I found this demo from one of the previous so you're already given some heights, right? Say you have an image that has table, that has some hutch, switch, and all that stuff, and some heights are already given there in that image. So this height gives you height of the objects that have already been calculated, right? Then in your case, so these are the actual heights, right? And then using your image information, you are now trying to, let me just take it there, find height.
On one height in the reference image, which you will see soon. And I would expect the other heights to be printed off when I do certain clicks. Right, so it displays the image first. Right, so this is just a living.
Just look at the captions. So it says click on 4 points to define 2 parallel lines, right? So these are 2 horizontal parallel lines.
Area, and it says click on 4 points to define 2 parallel lines, right? So this point, right? One parallel line, and it's darker here. So if I say this point and this point, right? And that's the vanishing point of these 2 parallel lines. Now, if I say, let's see,
That's for another set of parallel lines.
This is one line, and that's another vanishing point, and the line that joins
So
the
2 parallel lines,
So
2
what
set
is
of
it
parallel
now
lines give you 2
define-
vanishing points, and when you join those vanishing points,
now
you get a
define,
vanishing line.
another set of parallel lines in the vertical direction. Okay. So one vertical and this corner. Right, I'm not showing the vertical, which probably is down below, because it's going to be, the image is going to become very small. Right, so click on the top of the reference object. We passed it hutch. I basically call this as the hutch, here and here, right? Now it says click on top of the object to be measured, right? So I had the top of this cupboard, this, and this, okay.
There's a top one. Click on the top of the object to be
207.
measured, right? Now you have the reference height. You're trying to find out the
0.6,
find the height
right?
of the other object.
And yes, there is an error in the cross ratio one, but let's okay, so let's measure. Does anybody remember they're still written there, so I'll get back to the cross ratio one later. Just look at the first, the top one, that's the second algorithm, right? So the cupboard is 201 and the measured is 207. This is centimeters, right? And of course, these clicks are not perfect on the lines. Parallel lines have been defined based on only 2 points, and the vanishing points have been defined based on only 2 lines. So you need to increase that if you want more reliable measurements, right? So switch, right? So this is the light switch here and here. Height of switch is 155, and that says 130, right? Let me do that again, here, and base is here. Yeah, so just as accurate as the clicks, so it's a low resolution image, but it's getting fairly reasonable results. Right. This is table 65, and how much was the table up there? 75. Okay, let me stop this, go to working, but results the horizon. You see, in this case, so it's following closely. Here, the switch was close to the horizon, so incorrect. If it is well below, the second method is giving fairly good results. All right, so another height dot. What should I pass it on now? Reference. Which one?
So your clicking is very important. I said
Let's say cover
burst
the
detection
bigger
of points,
height,
right?
right?
So your clicking is very, very important.
So it starts
Right?
again.
Be very, very accurate if you really want to get the right heights. Okay, using the same procedure, using a different reference object. Let me just quickly move forward.
Right.
We get vanishing
It's
line.
also displaying the older one, but this is the newer calculation. So you can also see from here that how sensitive this could be to the clicking. You know, a few pixels can move your estimate. So it's always a good idea to estimate the vanishing lines and points based on multiple parallel lines. Okay, so now vertical. Reference object, we have given it covered. Top of the object, okay, let's say what is the hatch height. Okay, so that was 92 and 85. It's does anyone remember how much was the actual height? 95. So one of the techniques says 91, the other one says 85, right? So, and of course I mentioned the second algorithm is more robust. So the second algorithm is the first result here. Okay, so for better clicking, I just enlarging the image, and should have kept this image smaller, but I wanted to show the vanishing points, at least two of them. So the bigger the image, the more accurately you can do the clicks. So this is top of the switch, and then it's base. Now, base is tricky, you know, I don't know exactly where the base is, but I'm just having a go at it. Okay, so that was a pretty good click because the height of the switch is 130, if you remember. And the first technique is giving 132, and the second one is giving 126. And I think the second one is giving better. Okay, let's measure the height of the window. So it's performing a little bit better now. Yes. So as you see, it's not failing this time. So like I said, based on cross ratios, sometimes the first technique can give inaccurate results. The second technique is pretty good. Right, so that's all. So you want to do any other testing with this? Suggest something? First of all, you need to do edge detection. Edge detection. If you want to find